king minus man plus woman equals queen. You've probably seen this famous example of word vectors. But how does it actually work? How do you subtract a word from another word? The answer is embeddings, the mathematical trick that lets AI understand meaning by converting words, images, and concepts into lists of numbers. And it turns out meaning has geometry. A neural network is a sequence of matrix multiplications. It takes numbers in and produces numbers out. But language is made of words, symbols, not numbers. How do you multiply a matrix by the word cat? You can't. So we need a way to represent words as numbers. The naive approach? Assign each word a number. Cat is 1, dog is 2, house is 3. But this implies dog is between cat and house, which makes no sense. And the distance between cat and dog is the same as between dog and house, also nonsense. A better idea, one-hot encoding. If your vocabulary has 50,000 words, represent each word as a vector of 50,000 numbers, all zeros except a 1 at the word's position. Cat might be a 1 in position 4,237 in zeros everywhere else. Now no word is between any other. But there's a huge problem. Every word is equally distant from every other word. Cat and dog are just as far apart as cat and democracy. There's no notion of similarity. And the vectors are enormous, 50,000 dimensions for each word. Embeddings solve both problems. Instead of 50,000 dimensions, compress each word into a dense vector of, say, 768 numbers. But here's the key. Don't choose these numbers by hand. Let the neural network learn them during training. Start with random vectors. As the model trains on billions of words of text, it adjusts these vectors so that words used in similar contexts end up with similar vectors. Cat and dog both appear near words like pet, fur, veterinarian, so their vectors gradually move closer together. Cat and democracy appear in completely different contexts. Their vectors stay far apart. Meaning emerges from usage. Once trained, embeddings have remarkable geometric properties. Similar words are close together. Happy, joyful, glad form a cluster. Countries cluster together, verbs cluster together. But the most stunning property is that relationships become directions. The vector from man to woman captures the concept of gender. The vector from Paris to France captures the concept of capital of. So king minus man gives you the concept of royalty without gender. Add woman and you get queen. This isn't programmed, it emerges from training on text. The model discovers that gender, royalty, nationality, tense, all these concepts have consistent geometric directions in embedding space. The most famous algorithm for learning embeddings is Word2Vec, published by Mikolov at Google in 2013. The idea is beautifully simple. Take a sentence. The cat sat on the mat. Pick a target word. Sat. The context words are the surrounding words. The cat on the. Train a tiny neural network to predict the target from the context, or the context from the target. The hidden layer of this network is the embedding. After training on billions of words, this small network produces embeddings that capture deep semantic relationships. Word2Vec showed the world that simple neural networks trained on lots of data can discover the structure of language. Embeddings aren't just for words. Images can be embedded. A convolutional network compresses a 1 million pixel image into a 512-dimensional vector. Similar images have similar vectors. Sentences can be embedded. Sentence transformers compress an entire paragraph into one vector. You can search for similar documents by comparing their vectors. Users and products can be embedded. Netflix represents each user and each movie as a vector. If your vector is close to a movie's vector, Netflix recommends it. Even proteins can be embedded. AlphaFold uses embeddings to represent amino acid sequences. The embedding idea is universal. Take any complex object, learn to represent it as a vector, and let geometry capture meaning. In a transformer like GPT, the embedding is literally the first operation. The model has a vocabulary of, say, 100,000 tokens. The embedding matrix is a 100,000 by 768 table. Each row is the learned vector for one token. To embed a token, you just look up its row. This matrix contains about 77 million parameters, and it's learned end-to-end with the rest of the model through backpropagation. At the output end, the model uses the same embedding matrix, transposed, to convert the final hidden state back into a probability distribution over tokens. The embedding matrix is both the entry point and the exit point of the transformer. How do we mathematically measure if two embeddings are similar? The standard metric is cosine similarity. It's the cosine of the angle between two vectors. If two vectors point in the same direction, cosine is 1, maximum similarity. If they're perpendicular, cosine is 0, unrelated. If they point in opposite directions, cosine is -1, opposite meaning. The formula cosine similarity equals the dot product of A and B divided by the product of their magnitudes. This is how search engines work. Your query is embedded, every document is embedded, and the engine returns documents with the highest cosine similarity to your query. Next time we complete the picture with softmax and cross-entropy, how a transformer converts its final numbers into probabilities and how it's trained to pick the right next word. We're almost at the finish line. Subscribe and I'll see you in the next one.